Star one, I think. Do I ask if they can hear me? No.
No, they can't respond. Everybody's muted.
The broadcast is now starting. All attendees are in listen-only mode.
Welcome to today's webinar. Digitizing copper, applying IEC 61850 process bus to optimize P&C designs. My name is Leon Voskov with ABB Power Systems. I'll be monitoring today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question during the event, please use the question box on the GoToWebinar panel. We will answer as many questions as possible at the end of the event. Please ask your question during the presentation so it will be available by the end. Today's webinar will be recorded. A link to the recording will be emailed to you following the event. Feel free to forward the link to people you know could benefit from the presentation. This webinar is brought to you by Relion, by the Relion product family. And we'll go through a quick disclaimer. ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to the topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any action taken in reliance to the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Once again, today's webinar is on digitizing copper, and the presenter is Alejandro Schnikowski. Alejandro Schnikowski graduated from Florida International University in Miami with a Bachelor of Science in Electrical Engineering. During his studies, he conducted research in the field of digital relays and centralization of protection functions within the substation. In 2002, Alejandro joined Busbar Communications, where he engineered, deployed, and tested Ethernet networks. In 2005, he joined ABB, where he contributed in a variety of roles from application engineering to management. Recently, Alejandro moved with his family to Raleigh, North Carolina to take on his current role as manager of application and support for substation automation products in North America. So here's Alejandro, and he will start the presentation.
Thank you. Good afternoon, everybody. I hope everybody is having a good day so far. And as Leon just mentioned, we're going to talk about the IEC 61850 process bus in today's webinar. I encourage you to use the GoToWebinar pane to submit your questions, and those would be answered as we go along during this presentation. So again, thank you very much for tuning in, and we're going to go ahead and get started. So for today's webinar, we're going to cover basically 5 topics. We're going to provide you with a brief introduction to IEC 61850. We're going to talk about the IEC 61850 process bus and the introduction to it. We're going to talk about the ULCA implementation guidelines for IEC 61859-2. Hopefully they'll make a little bit more sense, the relationship between the IEC standard and the ULCA implementation guidelines, which is what most companies are currently deploying at this point. We're going to have a discussion about the system architecture and some of the considerations that need to be taken when deploying these types of systems. And then we're going to talk about a project example, a project that we deployed in Australia based on IEC 61859-2 Light Edition, which is, again, based on the recently released UCA implementation guidelines for IEC 61850 process bus. So let's go ahead and get started. So for starters, let's just talk about IEC 61850 and try to put this webinar in context. And let's just go back, a few years back when our substation automation systems were really based on hard wiring and remote terminal units. So here we have a, let's say a typical substation that was deployed on a greenfield basis, let's say at the beginning of the 1990s, late 1980s. And what we would typically find is that you would have, and again, there's a lot of substations that are somewhat deployed in this same way today, but essentially you would have your circuit breakers, you would have all the copper wire from your circuit breakers going into a panel, and then that panel will contain, again, from there you would have more copper wire that will connect to the protective relays. And then you would have essentially a separate system in the form of a remote terminal unit that would monitor some of the quantities of interest that were coming from the switchgear, such as current, voltage, position of breakers. You would have connection to the closed coils and trip coils of your breakers or motor-operated disconnects to be able to operate your substation that way. Now, how this information got relayed over to a central SCADA system or your network control center was the topic of any of the protocols, serial protocols available at the time. But the key distinction and the key difference between this architecture and what we will see in the next couple of slides is the fact that the information that was obtained by the protection relays was not utilized or was not transferred to SCADA or to this substation gateway via communications. In fact, you needed to somewhat replicate some of that copper wiring so that your remote terminal unit would obtain the necessary information to display status information about breakers, currents, and voltages in a mimic board, and then send that information over to SCADA or your network control center. At the end, you would end up with somewhat replicated or duplicated wiring from the process to the relay and from the process to your remote terminal unit, which would be used for, SCADA purposes. Now we move on to due to, and this is more current substation automation system architecture based on either DMP or Modbus, where now due to advancements on microprocessor relays and enhanced capability that these devices have these days, or started to have in the middle of the 1990s, essentially we would use all the connections that we were bringing from the switchyard over to the relays in the form of status of breakers, trip coils, closed coils, currents, voltages. All that information was already brought onto the relays in the form of copper wires so that those protection relays could perform their protection functions. And then the idea was that, well, why don't we add the capability so that the relays can send that information over to our remote terminal unit or substation gateway, as it is shown in this particular slide. And that's actually what we ended up with. So now our protection relays have communications capability, the protocols. Some of the widely used ones would be DNP, Modbus, or 103. And the idea is that, again, from your protection relays, those relays already have all the process-related information. Why don't we just go ahead and make that available to our substation gateway, which in turn will be able to provide a visual of the status of our substation in the form of an HMI, a digital HMI. Okay. And now let's go ahead and move on to our next. And again, one of the issues I would say, or one of the details about this particular architecture is that, I mean, today DMP is a mature protocol, but back in the day, other than DMP and Modbus, there were other protocols that were not open source that were used. So sometimes there may be a need to convert from one protocol to another protocol, and that created some issues in the sense of integration. So earlier towards the late 1990s, the need arose to actually have a standardized industry-accepted protocol for substation automation applications that will essentially minimize some of the risks of integration. And what I mean by that is ensuring interoperability, or ensuring that two devices from two different manufacturers would be able to exchange information over an open source protocol. And in essence, that's what IEC 61850 accomplished from a substation automation perspective and from a client-server perspective, which is essentially the relays sending information over to a master station or a gateway that will present all of this process-related information in a manner that the information can be consumed in an HMI or a MIMIC, so that the operator of the substation could get a good understanding as to what the status of his system is. In addition to this, which in 61850 is called client-server, we actually introduced two different protocols. As part of IEC 61850-8-1, we have goose messages, and as part of 61859-2, we have sample measure values. And what these are is, in the case of goose messages, it is a high-speed communications protocol that enables the exchange of horizontal information from one relay to another relay in a real-time basis. And then 61859-2, it's actually a protocol that enables the digitization of current signals and voltage signals, and then the publication of those currents and voltage signals onto an Ethernet network for their real-time deployment, so that relays could operate their protection functions based on these digital messages rather than utilizing current and voltages that would be wired up in the form of copper wires from your current transformers and voltage transformers. And that specifically is the topic of today's presentation. And as we went over during our introduction to IEC 61850 webinar, goals of the standard include interoperability, the exchange of information between IEDs from several manufacturers, free configuration. The standard should allow the free allocation of functions to devices and support any philosophy of customer, whether it's centralized or decentralized type of system, and then long-term stability in the form of future-proofing the standard, follow process in mainstream communications technology. What that means is essentially have a standard that would have a structure such that any changes on, let's say, communications media would not affect or would not slow down the process of the standard. So today, standard media that IEC 61850 prescribed is 100 FX, which is Ethernet fiber optic with a bandwidth of 100 megabits per second. The idea is that if a few years from now that changes to something else, the standard is flexible enough that we'll be able to prescribe or recommend that type of media as well, so that the standard continues to evolve with the rapid changes of technology. And the structure of the standard as such is, was put together in different sections in such a way that this evolution is facilitated. So now let's talk about the process bus. So the process bus is in essence a communications network at the process level, and we'll see some pictures in the next few slides to really illustrate that. In essence, this communications network is responsible for publishing quantities related to the process. In the case of electrical substations, we're really talking about voltages and currents. IEC 61850-9-2, which is the part named 9-2, defines the mapping of sample values over Ethernet. So if you were to go ahead and get a copy of IEC 61850-9-2, all it essentially defines is the protocol mapping from, how we're going to publish these samples and what is the type of addressing scheme that is necessary to publish it over an Ethernet frame. And when we talk about sample values, we're referring to current and voltage samples obtained from CTs and VTs, whether they're conventional or non-conventional. And we'll talk a little bit about that later on in the presentation. And IEC 61850 defines the communication protocol over Ethernet that enables the publication of such samples for the purposes of protection, monitoring, and metering. And in the case of protection, monitoring versus metering, there are some slight differences that we'll touch on when we talk about power quality type applications. So if we want to take a look at a visual of a sample architecture, what we have is essentially a relay in our control house, which it's host to several protection functions. In the case of, let's say, line protection relays, we may have a impedance element and we may have a line differential element, for example. And today, our current signals will be hardwired via copper from your VT onto the relay, and then the same would be accomplished with our CT or our current transformer. There will be copper wire from our current transformer onto the relay. And then based on those currents and voltages that have been stepped down to secondary quantities, the relay essentially samples, those signals, and then based on that, it runs its protection algorithms. And that is actually the picture that we have here on top of a conventional installation. When we talk about the IEC 61850 process bus, essentially what we have is, again, you still have current sensor, you still have a voltage sensor, which may be conventional or non-conventional, but now we're introducing another device, and that device, it's what's called a merging unit. And essentially what that merging unit does is it's going to sample the current and the voltages, and then it's going to publish those current and voltage samples via an Ethernet network. And now our relay, instead of obtaining the current and voltage information via copper wires, it's obtaining that information in the form of digital messages over an Ethernet network. So, what is a merging unit? Well, a merging unit, just so that we define it a little bit more, you essentially, in this picture, we have phase A, phase B, and phase C. And what your merging unit is going to have is somewhat similar to what a relay does today. There's going to be wiring from your current and voltage transformers onto the merging unit. Merging unit is expected to be very, very close to the process, whether it's inside the circuit breaker cubicle or somewhere adjacent, so that the wiring is minimized. And the merging unit essentially is going to have Ethernet out, an Ethernet port that it would use to publish this individual current and voltage samples. And we will see later on in the presentation what one of those Ethernet frames look like. But in essence, what we do is we are sampling, the merging unit is sampling the individual current and voltage signals, and each one of those samples are being used to form an Ethernet frame which contains these samples. They're published, and then the protection relays are able to subscribe to that message and use those samples to run their protection functions. Okay. One of the important considerations that need to be taken here is that if, let's say, you have one merging unit that you're using for, let's say, in the case of a ring bus or breaker and a half installation, where you may have two merging units publishing information, but one IED that's subscribed to those two data streams, there needs to be synchronization, because obviously the signals need to be processed by the relay in a synchronous manner. And for that purpose, 61859-2 has standardized format as to how we're going to synchronize those signals. And essentially the signals are time-stamped with a definite time reference source that can be found inside of the substations. And we'll talk more about the specifics on that in a later slide. So now we take a look just, the control house layout from a process bus perspective. What we find here is at the process level, we have our current and voltage transformers. And this would be essentially a conventional design where from my current and voltage transformers, I have copper wires that go into my panel inside my control house. And the relays essentially operate based on those signals. There's also copper wiring that goes from the relays onto the switchyard to operate the breaker. Then if we go to a 61850 process bus type architecture, what we're going to find is that from your current and voltage transformers, there's going to be connections to your merging unit. And then from the merging unit, there's going to be an Ethernet network that's going to be used to transmit this current and voltage samples. And then the relays inside our control house would be able to subscribe to those data streams and operate its protection functions based on that. And then there will also be, it could either be conventional wiring over to trip the breaker, or it could be via goose messages based on the capability that the circuit breaker has. So the process bus is a communications network at the process level, as mentioned, and also connecting the process to the bay level. IEC 62159-2 describes the transmission of sample analog values over Ethernet. And as you know, and as I mentioned, IEC 61850 also allows the transmission of binary data on process level via goose messages. Okay. Sample analog values are transferred as multicast, as Ethernet multicast messages, and can be received by all IEDs on the same network based on the configuration of that network, of course. The receiving IEDs decide whether to process the data or not. And what that means is that is the process that the relays use to either subscribe and consume that information or not subscribe and decide not to consume that information. The transmission of time of the messages on the network is not deterministic, which means that a time reference is required to align samples from different sources. Again, going back to a case where you may have a breaker and a half scheme or a ring bus scheme where there's going to be two merging units, there needs to be a source of time synchronization for those two merging units and your relay, so that those samples can be individually aligned at the IED level and the IED can perform its protection functions accurately. So IEC 61859-2 allows protection relays to operate based on digitized current and voltage signals that are distributed on a communications network in the form of Ethernet frames. Voltage and current signals from different CTs and VTs are published on the network and available to all devices that are connected to it. And this is one of the big advantages where on a conventional system, you may need a separate core to each individual relay that's going to be connected or that needs to consume that particular current signal. In the case of IEC 61850, you could use a single core associated with a merging unit, and then there is no penalty for the amount of devices that are subscribed to that sample measure value data stream that contains that current signal. And what that allows you to do is that you can have, in a more economical manner, more devices subscribed to current signals from a particular current transformer. Okay. And galvanic CTs and VT inputs are no longer necessary from that perspective. And what this results in is that you now have an isolation at the back of the relay from the primary equipment, which results in a safer installation and also, of course, results in wire reduction. At the same time, the IEDs are actually leaner because you do not, the IEDs will not require to have transformer boards or other components that are currently needed when processing current and voltage signals from, from conventional instrument transformers. It's also important to know that your current transformers and voltage transformer signals are processed by the merging unit, an intelligent device that samples the current and voltage signals, creates their digital IEC 61850 form, and publishes them on the network. So this is a basic summary of what we just discussed. So what are the standards that are really influencing sample values? And then there's really two standards or two documents that are important, or there are good references. And the first one, of course, is the 9-2 part of IEC 61850, and there's significant level of detail in this document in regards to the specific mapping of data onto an Ethernet ISO 8802-3 frame. Okay. At the time of its publication, it really left a lot of I would not say ambiguities, but it was very open for implementation. So the issue is that interpretation of one vendor may have resulted in something that may not be compatible with implementation from another vendor because the definitions in the standard were not too strict. So the UCA International User Group came out with to fill that gap, essentially the sign a document referred to as the implementation guidelines for 9-2 or for 9-2 LE, standing for Light Edition, which makes essentially makes much more stricter definitions in regards to what sample values protocols should be. And I'm going to talk about some of those specifics in the next couple of slides. But if you have access to the internet and to google.com, you could Google UCA 9-6159-2 implementation guidelines, and the document it's available online, and it's fairly easy to read. It's about 35 to 40 pages. So what are some of the things that the 61850 9-2 standard define? Well, first one, which is obviously essential if you're going to have devices from different manufacturers communicating via this network, is you have to define a sampling rate. And what the 9-2 LE implementation guidelines defines is that you must have 80 samples per cycle for protection applications, and then 256 samples per cycle for power quality type applications. What we've seen so far around the world is that the implementations are really looking at are inside the protection and control domain. So what I've seen so far, in my experience, is 80 samples per cycle type systems. Then another issue that came up was in terms of the configuration of the data set that was contained inside a sample values data stream. And the definition that the implementation guidelines makes is that each Ethernet frame, each sample values Ethernet frame will contain a data set which is composed of 3 currents for A, B, and C, plus a neutral current, which is 3I0, and then 3 phase voltages, meaning phase A, phase B, and phase C, plus 3V0, your neutral voltage. So what that in turn allows manufacturers to do is to design merging units, design IEDs that can consume this type of information. Another topic that was up for discussion and not really defined inside 61850 was the source of time synchronization. And what the 9-2 LE implementation guidelines prescribed is the utilization of optical pulse per second, or 1 PPS, as the standard time reference for a sample measure values implementation. And then the other essential definition inside the implementation guidelines was the definition of the logical device merging unit, where now inside the implementation guidelines there's specific rules for the logical device name and contain logical nodes. And this is obviously important from an engineering perspective. Okay, I'm going to go ahead and, because this is now, I have a couple of questions here that I'm going to address now that have come up. And first one, which is probably, this is a very, very, very common question. Is there a chance that you will face network congestion in large substations using analog and binary 61850 process bus? Are VLANs supported? So just from a technical perspective, when we talk about 6150 sample values protocol, we're really just based on the implementation guidelines of the UCA group, we're limiting ourselves to 4 currents, 4 voltages. There's no trip signals that you can embed in that datagram. For that, you would need to use 61858-1 in the form of goose messages. So based on our experience of real experience in terms of projects that we've deployed worldwide, what we're seeing is that you really would want to have a bandwidth allocation of about 4 to 5 megabits per second per IED. And given the fact that the prescribed media for these types of installations is 100 effects, you can make the math in terms of how many devices you can have inside of an unsegmented network. What I mean by unsegmented is one that does not support virtual LANs. 61859-2LE does support 802.1q, which is the protocol for virtual LANs. So yes, you would be able to segment your Ethernet network based on VLANs as well, so that you can limit or make better use of your network bandwidth. So I hope that answers that question. Okay, so now let's take a look at let's actually take a look at our datagram. Okay, all right. So if we take a look at the data, if we take a look at the Ethernet frame, just some definitions for, this is essentially a lot of information that I have here in this slide is just essentially standard for an Ethernet frame from any protocol, whether it's DNP, whether it's Modbus, or whether it's ICMP, for example. But essentially, you're going to have a preamble, you're going to have a destination MAC address, which in the case of 9-2 or in the case of goose messages is what's known as a multicast address, which means that if VLANs are not used, this is a message that will be heard or will be relayed to all the ports on a switch, if we want to put it on very basic terms. Okay, you're going to have a source address, which this address is actually the hardware MAC address from the device that's publishing this information. Then you have the 802.1q protocol tag priority, whereby we have here information in terms of the priority and VLAN ID. Then we have 2 octets for what's known as the ether type, or the type of protocol that we're essentially encapsulating as part of this Ethernet frame. And in the case of 9-2, we're looking at 88BA ether type. Okay. Then we're looking at the ether type app ID, which is 4000. And then we actually have what's referred to in Ethernet lingo as an APDU, or Application Protocol Data Unit. And essentially, the APDU is the sample values related information. And that's what we see here in this next slide, where essentially inside of our APDU, we have an Application Service Data Unit, which includes information such as the sample values ID, which is the sample values identifier inside of the network, This is something that's expected to be unique so that you can identify this data stream out of your merging unit. Okay, you're going to have each data frame, and this is important, is going to contain one sample of your phase A voltage, phase B voltage, phase C voltage, neutral voltage, phase A current, phase B current, phase C current, and neutral current. So when you just look at an individual line-2 sample values Ethernet frame, what you're going to find is essentially 8 samples. One sample for your phase A voltage, one sample for your phase B voltage, one sample for your phase C voltage, one sample for your neutral voltage, one sample for your phase A current, one sample for your phase B current, one sample for your phase C current, and one sample for your neutral current. And for protection applications, we're going to essentially send 80 frames per cycle because we're sampling that cycle 80 times, which results in 4,800 frames per second. So that's just to give you essentially an idea. And then if we take a look, and maybe in the, hopefully when you guys download the presentation, this picture is a little bit clearer. May not be too clear in the webinar based on the speed of your internet connection. But essentially here, what I'm showing is the content of the data set, which again, you're looking at the instantaneous sample for each one of the quantities that I just mentioned, phase A, B, C, and neutral voltage, phase A, B, C, and neutral current, and a quality attribute associated with each one of those samples. So when you look at your data set, the data set is effectively going to carry 16 pieces of information. Okay? When we talk about time synchronization, as we've discussed, definitely time synchronization is something that's needed to properly align the current and voltage samples. And what the UCA implementation guidelines prescribes today is 1 PPS, which stands for pulse per second. The source of synchronization must have an accuracy of plus minus 1 microsecond. And without getting into too many details, the IEDs are given a small period of time to write through any transient loss of time sync. This is based on the magnitude of the drift of the IED's clock. So what that means is that if somehow an IED loses transiently is time synchronization, there's actually a flag, a time sync flag that could be set to false or to true, and if it's set to false, obviously the sample is disregarded. But if a merging unit, for example, loses time synchronization, that merging unit is going to be allowed to continue to transmit its samples for a certain amount of time. And that set amount of time is based on the drift, on the magnitude of the drift of that clock of the merging unit. Okay, so let's talk about a practical. Project that ABB just delivered, and trying to look at this from technical perspective and the topology of this particular system, so that hopefully some of this information makes a little bit more sense. But essentially, PowerLink, which is a utility in Queensland in Australia, we're looking at a 275 kV substation. Okay, and the idea was to upgrade a ring bus section of that substation with IEC 61859-2 LE, so that it would be a process bus installation. And this installation was completed, handed over to the customer in December of 2011. So if we take a look at one line of this substation, what we essentially have is, again, it's a ring bus where we have 2 lines and 2 transformers associated with it. We have 1, 2, 3, and 4 breakers associated with our ring bus, of course. And then these boxes right here that stand for CP, these are your current voltage sensors, which are essentially across the circuit breaker. So we actually end up with a total of 8 sensors that we will have information available for. And then if we were to take a look at, for example, this architecture that was used, we have, for example, this. We have in essence this circuit breaker right here and one merging unit, and that merging unit is in turn connected to actually 3 sets of sensors. So this merging unit actually has the capability of publishing sample values for up to 3 sets of sensors, and then that information is in turn published to the different protection relays. Okay, we have a second merging unit here that also has this capability. We have a third one, and then we have a fourth one for a total of essentially 4 merging units that will be publishing all of this information. And this is for the purposes of providing differential protection to the 2 transformers, protection for each one of these lines, as well as control of each one of the different bays. Okay, in our particular system, the whole system was actually redundant. So when we look at the architecture, we actually have 2 networks. We have the process bus network close to the process, and then we have the station bus network for 61858-1. So essentially, as we could see, we have this process bus network which is connected to the different CP sensors and the different merging units, which are used to go ahead and publish all the different current and voltage values out of our ring bus installation. These 4 protection relays were the ones providing bay control capability for each one of the breakers, and then these devices right here were providing some were providing differential protection for the 2 transformers, some were providing differential protection for the 2 outgoing lines out of that substation, and then we had a bus differential scheme based on a distributed REB 500 scheme. So as you can see, this network right here is essentially segmented from our station bus, which was used for goose messages, for transmission of goose messages, as well as client server information over to our 2 RTUs, as well as our station HMI. So when we take a look at the different products that were involved here, we have the CP sensors, which is a combination of current and voltage sensor for GIS breakers. We have our 9-2LE merging unit, and then we have the IEDs 670s. In the case of the IED 670s, we have the capability of receiving current and voltage signals from both 9-2 as well as conventional current and voltage transformers, because low voltage side of the transformers for differential protection did not have sensors connected to the merging unit. So that's why we actually had a combination of conventional currents into the relay, as well as sample values for the current contribution from the high side for the differential protection of the transformers. Okay, we had the REB busbar and breaker failure protection for our ring bus scheme, and again, this got its current information from the different merging units and CP sensors. And in the case, a little bit of information about our main merging unit. This was the world's first UCA certified merging unit, which interfaces with the CP14 and CP3 sensors, and each merging unit has the capability of up to 3 three-phase measuring points. So that's a total of 9 analog quantities, and this obviously provides significant reduction of components for breaker and a half schemes, for example. and we have this particular merging unit has multiple Ethernet ports, so that there's a reduction in the need of Ethernet switches in protection circuits. So you could essentially utilize your different the different ports in your merging unit to create your process bus network without the need of additional switches. In the case of this particular system, the merging unit interfaces with the CP14 and CP3 sensors, which these are non-conventional instrument transformers, essentially based on Rogowski coil and capacitive dividers for voltage. Okay, so these are non-conventional instrument transformers for that sense that are available in GIS, gas-insulated switchgear, that ABB offers. So from this non-conventional instrument transformers, they would interface with the merging unit, and then the merging unit would go ahead and publish the different voltage and current samples. Okay, and this is just a basic view. You could have up to three-phase sets of analog quantities into our merging unit, and then there's independent 5 Ethernet ports to feed information for up to 5 different relays. Okay. The time synchronization used by the merging unit is based on, it's essentially based on TPS, just like the 61859-2LE implementation guidelines from the UCA group prescribed. Okay, and in the case of this particular system, essentially we had full redundancy up to the sensor level. So sensors were not redundant, but the electronics on the sensor are redundant, which then allowed us to interface redundantly to two different merging units and 2 different sets of relays, set A, set B, process bus network. And as described, I mean, this same concept was essentially applied for this ring bus, where we did not really, at the process bus level, we did not use Ethernet switches. We used the available ports on each one of the merging units to feed information off to each individual device. Okay? And just to now, if we put it within the context of protection and control, for line protection, we essentially had, for this line, for line 1B, we essentially had one bus differential relay that obtained its current information from this merging unit. This merging unit had current information from this from these 3 CP sensors. Okay, in the case of the Bay controller unit, again, it obtained the information for the complete bay from these 2 CP sensors. And then in the case of the line differential relay, there was obviously a fiber optics connection for the remote terminal of that line, but it also obtained its current samples from the merging unit out of these 2 CP sensors, T2 and T3. Line 2 was essentially a copycat of that particular scheme. And then in the case of the transformer base, what we had was, again, this T1 and T2 sensors going into the merging unit, as well as this A40T1 for the purposes of breaker fail, again. And the merging unit provided the RET670, which is the transformer differential relay, the current samples from the high side of the transformer via sample values, but the low side of the current contributions to complete the transformer differential protection scheme came in the form of conventional instrument transformers onto the relay. So the RET670 actually combined conventional with non-conventional current signals, meaning sample measure values, signals from the high side, and then just conventional hardwire instrument current transformers into the relay for the low side contribution of that transformer. And then let's talk real quick about the impact of these types of systems on protection and control testing. So we're used to using test switches to isolate the relay with your instrument transformers, with VTs, CTs, as well as all the different control signals, whether it's inputs onto the relay or outputs from the relay onto the rest of the system. So now if you have a device that takes sample values input onto your relay, how do you go ahead and test for that? Let's see. Okay, so so in the case of actually testing for these types of systems, where you actually, this day today available on the market, there's actually from the 3 major relay tested manufacturers, they have 9.2 LE implementations available in such way that you can test 9.2 relays, today with the use of, secondary injection via sample values in the form of Ethernet frames. So that is something that's very important, obviously, for the maintainability of the systems. And the good thing is that a lot of the interfaces are very, very similar to what to what a double 6150 or an Omicron CNC type device is. The only difference is that instead of having to wire voltage and currents to the relay, you essentially connect an Ethernet cable onto your network, and then you're able to do your testing that way. It is also important to mention that the 9-2 LE implementation guidelines offer a test bit in such a way that if, let's say, you use your tester to inject sample values onto the network, those sample values will have a test tag, and then it is based on the behavior of the device from the manufacturer how it would react to it. But that is something that could be used to indicate that those sample values are coming from a test device, so that the devices, if they're only told to do so, they should not react to that information. So that's something that's quite important to take into consideration for the maintainability of the system. And then from a maintainability perspective as well, there's already several applications or visualization tools that allow you to see and visualize your currents and voltages based on sample values in your computer, and phasor diagrams such as like an oscilloscope for voltage and current values based on sample values. So from a process bus perspective, I mean, there's definitely 3 benefits that need to be highlighted, and one is the increased operational safety due to the isolation of the galvanic connections onto the relay, which are now in the form of fiber optic cables, reduced lifestyle cycle cost. You have a permanent real-time system supervision, which increases system availability by increasing maintenance cycles and reducing outage times. What this means is that you're going to have redundant electronic parts to your sensors. You're able to monitor whether the sensors have failed, whether the mirroring unit have failed, and whether your protection relays have failed or not. So the capability of monitoring the device up to the primary sensors is certainly increased. And then obviously there's the savings in regards to copper cabling. Of course, this is a new technology, and this is something that requires a learning curve to get the necessary personnel trained and with a good understanding, of what the technology offers and what are the different intricacies of the side. But these are definitely some of the benefits that have been materialized in some of these installations. So with that in mind, I just want to mention that this webinar was brought to you by the Relion product family, Advanced Protection and Control IEDs from ABB. Relion, think beyond the box, designed to seamlessly consolidate functions, Relion relays are smarter, more flexible, and more adaptable, easy to integrate, and with an extensive function library, the Relion family of protection and control delivers advanced functionality and improved performance. And with this message, I'm going to go ahead and jump onto whatever questions we have in the queue. So let's see what we have. Network congestion. Okay, so I have a question here that says, what happens when the allowable drift time expires? So I think this question goes back to my comment about the time synchronization, where I mentioned that the standard now defines a behavior if, for example, a merging unit loses its source of time synchronization. And there is a write-through time, if we want to put it on those terms, once that happens. Once that time expires, or the allowable time expires, and that time again is based on the drift of the clock, the samples published by that merging unit will have a false in the flag associated, in the flag of that Ethernet frame associated with time synchronization. And based on the design decisions that were made, that would in turn potentially make the relays disregard those samples. I have another question here which says, is the 61850 being used for transmission as well as distribution? And 61850 really, at least when we refer to protocols, we're really talking about client server, which is something similar to DMP within the substation. It refers to goose messages, which is the high-speed or real-time exchange of information between relays. And then it also relates to the topic of today's webinar, which is sample measure values, or the process bus. And we have found around the world installations at both transmission, distribution, as well as generation plants. Does the 61850 standard mandate A, the use of the test bit, and B, how the device will react when receiving a message with the test bit set? That is an excellent question. And actually, in the case of the 9.2, implementation guidelines, the application of the test bit is being deemed as I'm sorry, I run on a blank with the word, but it's not mandatory to implement it. Okay, and then the standard also does not define what the behavior should be. That is something that's being left off to the different manufacturers. So it is definitely something that, in the form of specifications or evaluations of your different products, you as an end user have to take into consideration, because it's something that's definitely important from the perspective of maintaining the system. What I would share is that there's an ongoing initiative to explore this topic in depth, to finally have much stricter definitions as to what that behavior should be, because again, it's something that is extremely important. We have a question here that says, can I have the PowerPoint slides? And the answer is yes. We'll go ahead and email those to you. Also, just want to remind you that all of this webinar is being recorded and will be available in our YouTube channel. Okay, and there's also a question here that we have, how many substations have been applied, upgraded to IEC 61850 standard in the world? We can certainly send you a reference list case, at least from an ABB perspective, but it's up in the hundreds of projects that we have delivered. From a process bus perspective, since the 9-2LE implementation guidelines were not published until somewhat recently, I would say that there's a few. I would say that Alstom Grid has a solution for this. ABB has a solution for this, complete end-to-end solution. So those are, as I understand, those are the two main companies that have deployed projects, end-user projects worldwide. There's also actually a very interesting project that's being commissioned by CFE in Mexico, which is actually a multi-vendor 9-2 installation, and that's actually been a very successful pilot project that has included collaboration from all different vendors, and it's been something that we have had a great pleasure of being part of. And again, participation from all major vendors of IED products. But we can go ahead and send you a reference list for those projects. So if there are no more questions, I would like to thank you again for your participation on today's webinar, and we look forward to having you on any future sessions. Thank you very much, and have a